So getting everything ready here. See more and more people joining in, so that's good. We have see that we're already approaching the 60 participants, and the number is slowly increasing. All right, great. So it's almost time to start. Let's see a lot of people here. Wonderful. All right, it's time to get started. So hello everyone. Welcome to our special interest group workshop for geotechnical analysis within Bentley. And today I'm going to talk about dynamics and seismic features in Plaxis. And my name is Micha van der Sloot. I am the Senior Manager User Success for the geotechnical department within Bentley Systems. And I'm mostly dealing with the Plaxis finite element solutions and limbed equilibrium solutions. So today's event, it will approximately take about 60 minutes, and I hope I can squeeze in some time to answer your questions. The SIG webinar will be recorded. A few people already asked. It will be recorded and it will be available on demand on our Learn server. I'll already shared the link in our chat. If you have been present today, you will be awarded a personal development hour or learning unit in your Bentley transcript. I'll show in the next slide how that works. If there are issues with that, please contact bentley.institute@bentley.com. And schedules you can find in our Bentley communities on communities.bentley.com and then search for Plaxis. The certificate, please allow a few working days before it's being applied and posted to your account. You can go to learn.bentley.com/transcript where you can find the link, direct access. Please make sure that you have registered under the same email address as the one that you have in your Bentley account. So go to ims.bentley.com if you do not have one. And that means that we can have, so then automatically these certificates will be added to your learning history, and you can download also the certificate and it will look like this. During the session, if you have any questions, please use the question box. So if you look at the bottom, you will see a menu option like this. There's an option for chat and for questions. If possible, please use the questions box. That's more organized for me to answer your questions when we have time to answer questions. If anything is happening during the session in the chat, I'm not always able to solve that through the chat. So if you have questions, please add them to the question box. I'm afraid the microphone is not open from your end. We already have about 130 people present, so that might be a bit too overwhelming during the presentation if there are too many people having questions verbally. So if you have questions, please add them to the questions part. So today's topic, seismic features and dynamic features in Plaxis. So I'll give a quick introduction of what we can do with seismic and dynamic calculations. And And today focus will be on selecting dynamic boundary conditions, how they work, the loading input and accelerogram definition. So somehow you have to get some kind of motion into your analysis. That can be done through loading by activating a load that varies in time, or maybe you have an accelerogram or some displacements in time that you want to put in. How do we do that? We'll go over to that. And then something on time stepping importance, mainly focused to the loading input and accelerogram. And then I have a summary also with some pointers for things to also pay attention to in your dynamic analysis. So what type of dynamic problems can we solve using that we are interested in while doing geotechnical analysis? We can think about induced vibrations. So this can be done by mostly human sources. And you can think about machines. So if you have a big machine and then you switch it on and it starts to vibrate. And think about a generator, but also wind turbines also, of course, will have some vibrations due to the wind loading and the wind turbine circling. If you have construction works, you have drilling or blasting. Um, Also traffic loads, of course, also a very big source of vibrations. And whenever we have traffic moving over a bridge or over a road, trains moving over a railway track, or metro trains moving through a tunnel, these are all causing vibrations that will go into the soil or have interaction with the soil. And then we want to see what's happening there. So there's a vibrating source that goes into the ground. And as you can see also from these inputs, they have usually a quite regular signal, and maybe for a short period of time, but it's usually quite regular. If you think about machine vibrations, wind turbines, they usually have a very strict period in which these signals happen. If you talk about earthquakes, these are, of course, coming from a seismic event, and they happen deep underground, and then they actually going to these pressure waves and shear waves. They will move towards the surface, and the structures, which are, of course, in the ground or on top of the ground, in which you will have the interaction there. And that's also where usually the interest of earthquake engineering comes, of what's the effect of a seismic event on the safety or the performance of your structure. As you can see also here in these two signals, one is in time domain, and that's the image in the middle. And if we look at the right hand side, it's one in frequency domain. You can see these are very irregular signals. So that's also quite different from the induced vibrations. So what type of issues do we deal with typically in geotechnical practice? Of course, wave propagation. So how does the wave travel through the medium? So we have to think about stiffness of the soil material. Is there reflection? Where does the source come from? Then we talk about inertia forces. If you have a big structure with a lot of weight, of course, there will be a lot of inertia forces that will have an influence on the deformations of the structure. Um, Things like cyclic loading also might have an effect on your the soil characteristics that you're dealing with. And maybe due to the cyclic loading, you will get densification, or maybe we'll have an accumulation of excess pore pressure leading to liquefaction. Um, Also, if you have some kind of distance between the source and the part that you're interested in, it can lead to, you have to take into account damping, because of course, while the wave travels through the medium, it will lose some energy. Both could be due to material damping, also or radiation damping, because the wave happens in 3D space. So not all the energy from the source directly goes to your structure, for instance. That's typically the case when you're dealing with human-induced vibrations. If you think about earthquake loading, of course, these events are so big that the zone that you're interested in will get the same type of um, um, energy from the seismic event in that specific location. So one important thing in our finite element calculation, or with modeling in general, is your boundary conditions. So if you think about boundary conditions, of course, we model the reality, which is that's very, very large. But when we want to make a model to see what's happening, we want to investigate and assess the effect of such seismic or dynamics event, yeah, we take a small part of the real world. Now, if you think about waves that occur maybe from the crest of the dam here, the waves that will travel to the left and to the right. And of course, in reality, the reality doesn't know there's a model boundary here. And it's just an artificial boundary that we choose to limit the size of our finite element mesh. Here, in reality, the waves travel past this boundary. Now, if we have a model, we do not do anything special. We have our static default fixities, which means here we have no horizontal deformations on the lateral boundaries. And it means it's a fixed boundary. And actually, when a wave hits the boundary here, it will be reflected 100%. Of course, this is not what we have in reality. In reality, we do not have a wave that goes away from the dam and then bounces back for no specific reason. Rather, so the solution that you can have, of course, is that you have a boundary that will absorb this energy from the wave such that it will not reflect back into the model. And it will not disturb the response of the dam in this case. So Leismer and Koolmeyer created absorbent boundaries for finite element calculations. It's a simple method with reasonable accuracy. And basically what it does, it is, instead of having a fixed boundary, it's including dashpots on the boundary such that the wave that's coming in will be absorbed by these dampers. And we can have dampers in the perpendicular direction to this boundary, but also in the direction of the boundary. So we can see here which one is perpendicular, and here which is parallel to the boundary. So we have these two dashpot directions here. And this gives us reasonable accuracy. So these viscous boundaries, these are used absorbing waves leaving the model. So we have a signal inside the model, something happening inside the model, and then when the wave wants to leave the model, it can be absorbed by this boundary. And these viscous boundaries, they work perfectly when the body waves are perpendicular to the viscous boundary. Basically, it means that at the boundaries, we should have some kind of one-dimensional wave propagation, so that's only in the horizontal direction. It can still be used for inclined waves if the angle of is less than 60 degrees, then we can still use them. If this angle of incoming waves at the boundary is larger than this one, then these boundaries are not so good. If you have a seismic analysis, we can use this viscous boundary, but they have to be placed very, very far away from the part that you're interested in order not to disturb the analysis. And also, I'll come back to that later, what you can do better. So it gives you a very large soil, large model width. You also have to include sufficient damping in the soil. There are some limitations here. There's permanent displacement possible if you have low frequency waves, because the low frequency waves happen so slow for these dampers that you will see permanent displacement. Also, if you have permanent static loads, of course, they will also give you permanent displacement. That also means they will, if you have a static load, it can also have an horizontal permanent displacement. That's the nature of these viscous boundaries. What we'll also see is that we can get large plastic strains in adjacent soil elements. That is typically to be seen, especially when you have large stress variations for materials which have a frictional strength. So based on friction angle, that means then when the stress is reduced, and that can happen when the soil starts to unload due to the wave direction, you can see that we'll get large plastic strains there, and also some weird behaviors on the boundary conditions if that happens. So that's also the reason why you should put the boundaries far enough away with sufficient damping to make sure that you do not have those large excitations on the model boundaries. Also, if you think about the vibration source, if the vibration source is inside the model, if you think about modeling a generator or traffic loads, this vibration source is inside the model. Typically, it's on the surface of the soil that you've modeled using your finite element calculation. We can then easily put absorbent boundaries at the left and the right lateral sides, and also at the bottom side of the model, so that actually all the energy is generated inside the model, and the viscous boundaries will absorb these at the boundaries, so that they will leave the model properly. If the vibration source happens outside the model, and this is typically the case, for instance, in an earthquake, the vibrations, you will have to apply them at a specific boundary. And it can be a load or something what we in Plaxis call a prescribed displacement. This prescribed displacement can contain not only displacement, but you can also specify them as velocity or acceleration. And we have to apply, of course, absorbent boundaries for all other boundary conditions. Now, if you look at the seismic analysis, the waves, they enter the model from deep soil. So that means actually the event happens way below the part that you're modeling, and then the waves travel upwards until they reach the surface. And we have to place our boundary somewhere. So there the seismic motion will come into the model. When modeling it properly, the left and right boundaries should represent free field behavior. So that means that there will be waves coming, should be coming waves out, but it could also be that the waves can come in because of the free field behavior. But of course, any disturbance that's happening in the main domain should leave here the model and not reflect, because that's not happening in free field. In reality, any wave that travels here from the center to the lateral boundary should actually leave the model. So those should be absorbed at the boundaries. Now, if we have a simplified model, the left and right boundary, we define them as viscous boundary conditions, which is the default option for dynamic calculations. There's a limitation there because the left and right boundaries, they behave rather independent. There's nothing that connects them in a certain way. They will just have these dampers at the left and right hand side of the model, and these dampers will just absorb the energy, and there's no relationship between the two sides of the model. In the simplified version, we directly specify the acceleration or the motion at the bottom of the model, and it's nice. Then this motion actually is being put here, and then the waves travel upwards. They will reflect from the surface down again, but because we specify here the prescribed displacement or the acceleration, actually the incoming wave will bounce off this element here, and we'll get some additional reflection here. So that means that also you get some disturbance after the signal has moved from the surface back to the bottom of the model, and then you can see that there will be some disturbance because of choosing this simplified type of boundary condition where the input motion is specified. If we talk about the predefined boundaries, the viscous boundaries and prescribed displacement, so what I showed you in the previous slide, it has limitations for a site response analysis or earthquake event. And I mentioned them in previous slide, these independent viscous boundaries and this rigid motion which is being defined at the bottom causing reflections. So in Plaxis we have these additional earthquake boundary conditions. We have tight degrees of freedom. That's the one that you can use if you want to do a 1D soil column. I'll show how that works. If you want to do, if you have a structure or you have a slope or you have a foundation where you actually want to analyze the effect of the earthquake on that structure, we'll need to have a combination of free field elements and a compliant base. So if we look at modeling a single soil column, if you think about, we just have a free field condition here, and we take this 1D soil column. The earthquake event happens here at the, we apply here at the bottom as an input, to maybe this signal, and it means the whole bottom will get this acceleration. If we take this one single soil column, of course it will get the same behavior. And since all of these soil columns that we can define here behave the same, we can assume that we can represent the behavior well if we can take a 1D soil column and make sure that whatever happens on the left hand side of the soil column also happens here at this edge. So you can see this is happening here. So we have a, with these tight degrees of freedom, we can have this single soil column. The dynamic load is defined here at the bottom. And what we can do is that we tie the deformations from the left-hand side to the right-hand side on every elevation, or in the final element calculation on every node. And that's shown here on this side of the slide. And you can see that the blue nodes, which represent the nodes on the left-hand side, and the white circles here representing the nodes on the other side of the soil column. These will be connected in the calculation, and it means that, for instance, if this node wants to move a little bit, let's say it wants to move 5 millimeters to the left, this also will move 5 meters to the left. And that's the same for all of these nodes on every elevation. In order for this to work, we must ensure that we'll have nodes at exactly the same elevation. And that implies that the two sides of the model should be having the same length, and at every elevation it should have a node on the left hand and the right hand side in order to work this. But with this we can simply represent a 1D soil column for maybe a 1D site response analysis, and then we can see also so then we can simply model this with very few elements. That means also the calculation will be relatively fast. And that's quite easy to do. If waves inside the model are moving out, they should be absorbed by the boundaries, which are the dashpots. But if we're dealing with an earthquake, the free field condition also implies there is a signal. If we think about here's our main domain, and here we have something that represents the free field. So this is this thick black line. Of course, also here we get this earthquake event that actually is going to have its waves traveling to the surface and maybe reflect back. So these free field parts should actually, of course, also will move. The same with the main domain, and these will, of course, should be connected as well. So what these free field elements will do, they will absorb different waves in the main domain that wants to travel through the free field to the free field elements. They will be absorbed by the dashpots. And any behavior from the free field element which should have an influence on the main domain will be applied as a additional load here on the main domain to make sure that it is in balance with the free field conditions. So that means the free field elements, they are defined here outside our main domain as specific 1D soil elements. They will get the same soil properties as the main domain. So if we have a bedrock, for instance, down here in the middle, we have some kind of sand, and the top of we have silt. The free field elements will take the exact same properties, same constitutive soil model, so the same dynamic response as the one from the main domain. So there's nothing that you have to specify additionally there. And the linking will be that that any differential, any influence of this free field will be applied as tractions on the model boundary of the main domain, and the main domain will get the waves into the dashboards to absorb the energy so that they can actually leave the model. Now, if we look at the bottom boundary, where we actually, that's of course the part where the seismic wave enters the model. We have two typical cases for the bottom boundary conditions. A rigid base. We can directly specify this acceleration time history. Or we can use a compliant base where we have an absorbing boundary that's used at the base of the Plaxis model, which works a bit similar as the free field element. So we can have basically tractions from the earthquake events, and this will be shear stresses applied on the bottom boundary if you only have a horizontal component of your acceleration. This will apply it as a shear stress, and that means that the wave can move upwards, and when the wave reflect on the ground surface and travel downwards again, they will be absorbed by these dashboards. So that means there will be no reflection. One thing to note here, especially about this one, is that the incoming waves here, this requires only the upward motion only. So that's something to take into account, that you only have to use the upward motion here, because that's the one that actually is going to travel upwards through these tractions, and any total movement, downward motion, will be actually absorbed here by the dashboards. As mentioned before, the compliant base is then better because it has no reflection, while with the rigid base, the downward moving waves will actually reflect on the boundary, and they will move back into the model again. So to summarize what you have to specify for a seismic model, so you can see everything here. So if our main soil body, so actually where we put the geometry, our soil layers, maybe you want to put a structure here on top. In order to have the seismic event going into the model, we will define an acceleration here. That's user input. Then this acceleration will internally be transferred to tractions on the model boundary here at the bottom, but also here in these blue free field elements. And then, so that means that then the wave enters the main soil body and the free field elements. And then using our free field elements here at the side, you will get the interaction between free field conditions and what's actually happening here in the soil model. This is the total picture that we can then define here for a Plaxis 2D, but also for Plaxis 3D analysis. So these are the different specific seismic, the specific dynamic boundary conditions, I should say. So first on the left, viscous boundaries. These are primarily used for induced vibrations inside the model. These are not recommended to use for earthquakes. In the middle, we have our free field and compliant based boundaries that you can typically use for earthquake analysis to get the seismic event traveling upwards into your main domain and these free field elements. And here, if you want to do a 1D site response analysis, that's the main purpose of the tight degrees of freedom. There's some other use cases as well. I will not go into details for those, but the typical case is a 1D site response analysis. There we can have a tie the left and the right hand side, and that means that the nodes on the left and the right hand side follow the same deformations, and so that means we can have a proper 1D soil column represented in the Plaxis to define element calculation, so that you can actually also use the Plaxis constitutive soil models to see the seismic waves traveling through the soil medium. Where can we specify these boundary conditions? So for a dynamic analysis, we can go to our Plaxis Model Explorer. You can find this always in your bottom left-hand side while being in stage construction mode. And there we have under model conditions, we have an option called dynamics. There we can specify the different options here. We have none. So that means the static conditions apply, so they will fall back to whatever we defined here in deformations. And that's typically always the default boundary conditions, which means fully fixed at the bottom, and the two lateral sides will have a horizontal fixity. They can move vertically. And that's of course when you do not override something with a prescribed dynamic displacement. We can have viscous boundaries. These are set by default for the lateral sides if you choose dynamics. We can have tight degrees of freedom. This is for the 1D approach, only available in Plaxis 2D. While using tight degrees of freedom, make sure that you set the horizontal lateral, that you set the vertical lateral boundaries to free. So this, the X-min, X-max deformation default fixity should be set to free. So that's something you have to do with tight degrees of freedom. For free field and compliant base, we can select them here. There's an additional condition. You have to specify interface elements at the inside of the model on the boundaries. So basically what you do is you draw a line, or in 3D, you define a surface, you apply an interface such that it will be on the inside of the model. So it will be between the model boundary and the soil. And then we have these free field elements there. So you can select them here to make sure that you have a proper seismic event. Now, if we talk about a seismic event or machine vibrations, of course, we have to specify how this works and what's the value in time for its dynamic loading. So if, for instance, if we take load, maybe it's a machine vibration that we want to specify. So in order for our dynamic loading, what we can input, we have a static component and a dynamic component. So if we look at the how you define a line load, so here is the one from the selection explorer. So if we just click on the line load, this is the part that we get. We have here line 1 and then line load 1, which this represents our static component. So this is the static component that will be applied in our plastic or consolidation phase, but also it will be applied in our dynamics phase. And if we look at the second part here, which is only the dynamic part, which only will be used in a dynamics type of calculation, it has two distinct components. We have here a load value and a multiplier. This product of those two, so the load times this multiplier, you can also see this here in this equation. So we have a value qy dynamic that represents this part here times a multiplier, and this multiplier is a function, or so it can be an harmonic function. We can also have a table input, and this is the part that can vary in time. And you can see it's shown here with the multipliers, and in this case it's a harmonic load with an amplitude and a phase and a specific frequency, and this is actually the loading value. So what's happening in the calculation is that you have a total load qy that varies in time, which is the static component plus our dynamic component times the multiplier, which can vary in time. If we want to do a machine vibration, typically what you do is that you first activate the machine. No, you define the machine. It's there already. That's a static condition. The machine is present already, so we can use a plastic calculation, activate the static component, and then at the moment that we switch on the machine, so it actually starts vibrating, is then in the dynamics phase we activate the static plus the dynamic components, such that we have the total load varying in time. If we look at the input motion, so instead of specifying a load value or a distributed load value, we can also specify an input motion. This works a bit similar, but also slightly different, because there's no distinction between a static and a dynamic component. If we are in a dynamics phase, our active prescribed displacement value, so in this case uxt, it's equal to our ux value, and you can see it here, for instance. And this is the prescribed value times our multiplier value, and this is our multiplier value. So it will just be the product of these two, and so you can see it completely varies in time for the for this part. One thing to note is that the multiplier controls more than just the value, because we also have an associated data type. This is in the multiplier, you specify if the input motion that you specify is a direct displacement that varies in time, or an acceleration, or maybe a velocity as well. If you specify an acceleration, the Plaxis calculation knows that, and it will use a time integration scheme to get the accelerations into velocities, and then the velocities, of course, will result in a displacement. So the data type controls what we're having here, although it still refers you to a displacement. The multiplier data type will specify it is being in motion, will be an acceleration, velocity, or displacement. As input, we can also have harmonic input, or we have a table input, and that's typically used when you want to do an earthquake, because if it's a very irregular signal, so we have the time multiplier data, we can directly import them from ASCII, or if you have the table in Excel, you can just copy paste the data directly into Plaxis. On top of that, we can also apply drift correction, and I will come back to that a bit later. But before we're going to talk about the input motion that we want to define for our model, it depends on a few things. Of course, where is the acceleration or accelerogram that you want to use in your earthquake calculation? Where is it recorded? Is it here, free surface motion? Maybe it's an outcropping motion, so it means it's recorded on top of bedrock that extends to the surface. As you remember, for the compliant-based input, we have to specify the upward motion. So the question is, if we have an outcropping motion on a rock, what kind of input motion do we have to give? Or if we have the free surface motion, what type of analysis do we have to do to make sure that we have a proper input motion that is the upward motion that we want to define? Now, if we have this rock outcropping motion, and this is a very common case that you have that, if you think about a rope, if you have a rope that you want to excite and actually move back and forth, the rope will show a sinus shape. And along the length of the rope, we have a certain amplitude. But what we see when we reach the end of the rope, actually the amplitude doubles. Now, that's also what we see when we have a linear elastic material like a bedrock, which has a very high stiffness, and so also a very high shear wave velocity. and you will see that the rock outcropping motion is twice as large as the upward input motion. So if that's the case, that's a very good assumption to get the input motion and divided by 2 to get the upward motion. That's a typical case that you can do. But of course, that assumes that we have the bottom for the input motion, that we have it inside our bedrock. Now, it could be that the bedrock is very deep. The question is then, should we then model it all the way down, maybe 200, 300, 400 meters down, and then we have all kinds of soft soil? Do we have to model that all those kind of soil layers? Well, actually, that will just add to the calculation time, because the more elements we have, the more calculation time we need. So in that case, you might want to choose smaller model dimensions. Then the question comes, okay, we need to have the upward motion at the bottom of our model. How do we get that? Now we can then get a deconvoluted signal. You can get it from a 1D site response analysis, where you actually model the whole soil column, and you will see what the upward motion would be in that case, and then you can apply it at the bottom of the boundary. We can do that in a 1D site response analysis using, for instance, the equivalent linear 1D analysis that you have in Shake or Deep Soil or ERA. We can also use Plaxis 2D, and then we basically model a soil column using the 1D site response analysis tool using tight degrees of freedom. Then we can also see what the upward motion would be if we model all these soil layers here with the different stiffnesses, different stiffness contrast. Maybe there's also non-linearity involved or material damping. Then you can model that as well. So once we have selected the proper upward motion that we want to apply at the base of the model, maybe based on regulations, you need to have some kind of signal, and you have to scale it in such a way such that it has the proper energy content, or that it has a certain peak ground acceleration. So what's happening here, so this is the input window of our displacement multipliers. So here we can define it as a table using, as you can see here, accelerations. Can apply the scaling factor, and the scaling factor can be a factor that we then can apply over all the acceleration values that we have here in the accelerogram, or we can specify it on the maximum value. So say in this case, we have a maximum value of -3. Maybe the regulations say that we should have a certain earthquake event with a peak ground acceleration of 4. So then we can actually have the scaling factor set the maximum value to 4, and actually Plaxis will upscale this by getting the maximum value up to 4 and then scaling all the other values with the same value. So that's an easy way to update that. Now, once we have accelerations, you can here also choose to see what the acceleration in time will be, but also what, if we have a time integration, what our velocities will be, and also what the final deformations will be. So it gives you also a good sense if the input signal that you have specified for Plaxis, if that fits very well. And you can also can see at the end if we have a drift correction. So I'll come back to that in the next slides. Another representation here is also more in frequency domain. For instance, Fourier spectra, response spectra, Arias intensity. So we can also then inspect the signal for those kind of different representations. Plaxis, of course, is a fundamental calculation that's being done in time domain. But of course, you also want to check how it's representing in frequency domain, because a lot of regulations and also from structural analysis, people tend to also want to look at frequencies. Something about the drift correction, which I already mentioned. We can have a baseline correction. The question is why? Why do we want to have a drift correction or something that corrects the baseline? Now, if we have the acceleration and we integrate this over time, we can get the velocities here. And the velocity, of course, then leads to displacement. But as you can see here, is that we slowly sort of drift away from the final zero settlement. Because at the end, usually you end up with zero settlement if you just have free field conditions. So this actually is going to have drift. But okay, of course, this is not something that we want to have in our analysis. So we can have this baseline translation of the raw accelerogram, and this can be caused by instrumentation errors, but also by digitizing errors or numerical scheme errors that will have a small influence for each time step, because we calculate so many time steps, actually, of course, this error compounds over time. Then we can have this drift correction to force our final displacement to be zero. What's happening in the calculation, we'll apply a very low frequency velocity to make sure that at the end of the analysis we have a zero displacement. So once we have specified our input signal, something that you also have to take care of in your calculation settings is the importance for the time stepping. Because during time integration, we can have some small numerical error if we do not properly interpolate the data points. And I'll show in the next slide how that works and also why. But it's good practice to define the dynamic analysis time matching such that the dynamic substepping matches the time discretization of the input time histories. What does it mean? Say that we have here our acceleration data. So we have every 0.02 second, we have a acceleration value. And we specify our dynamic time interval to be 40 seconds. So 2000 points equally spread over our 40-second dynamic time interval. So if you look at our numerical control parameters, when specifying our time step determination, the max steps and the number of sub-steps, these are actually the product of these two are the actual time steps being done in our finite element calculation. And with the max steps, that is the point where we can save the data points for the analysis. But the product of the 200 times 10, so these are the steps and these are the sub-steps. The sub-steps will not be stored, only the full steps will be stored. The product of these two is controlling the time step. So we have here 2000 points for 40 seconds, so 0.02 seconds for every sub-step. So this matches exactly with our input signal, so that's great. Now we can also increase the number of sub-steps. Instead of 10, we make 20. So actually here we have 4000 data points. This is also works also nicely because we all match the data points, and Plaxis will use a linear interpolation between the data points to get the acceleration at that time step. However, if we choose a different number like 17, 200 times 17 will then not match all the data points for these 2000 points. And the same if we make the sub-step smaller, so that we just have 1000 data points. Why is that? I'll show here. So here we have a case where actually we have an input signal time step 0.1 seconds, and also our calculation is also 0.1 second, so it's a perfect match. And you can see that for all the data points, actually the acceleration we use for our input motion at the base of our model is actually exactly the points that we have for the from the actual earthquake events. Second here is that if we do not match that, say that we choose our data points. So we have 4 data points in our accelerogram, while having just 1 point here in the calculation steps. Actually, you'll see that we miss these peaks. So actually, the extremes of our accelerogram will be missed. So that means actually we'll deviate from not only the accelerations, but then also the deformations at the end, because we miss these peaks. It will be sort of smeared out. And the same happens if we are in between the data points, because then Plaxis will interpolate. And you can see, for instance, what's happening here is that we miss this point here, but also this point here, and we're actually going in between data points. So also the effect will be smeared out. So that's why we should make sure that our input signal matches with the dynamic steps that we want to do. Now, something on the stored steps, which can also be important. If you want to do post-processing, so this is mostly important for post-processing, Plaxis will write output for all the calculation steps which are set to be stored. Dynamic substeps will not be stored. Max steps will be used for internal tracking of the calculation, and that also be used for nodes that you select prior to your calculation. But the whole 2D results will only be stored for these items here, the max number of steps stored. And these will, of course, will be equally divided over these max steps. And these max number of steps stored will be used if you want to, for instance, create animations, or you're interested in specific time points in time where you want to, for instance, analyze the excess pore pressure, or the stresses, or the deformations. So in order to do that, you have to make sure that you save enough of these steps for your calculation. Plaxis by default will only store the last. You have to increase it. If you want to create animations at the end, or you really want to go into details of the analysis for every time step, make sure that you set the max time steps equal to the number of additional steps. So this comes to the end of the analysis, where we talk about a few of the dynamic features that we have in Plaxis. A few topics that here I want to highlight, because these are equally important as the ones I discussed here today, but we did not have time enough to fit this in a 1-hour webinar. Soil stiffness is very important. While dealing with soil stiffness, you have to realize that we have static stiffness, which sort of comes from engineering practice, where we actually calculate foundations or deep excavations, embankments, which have relatively large strains happening. But in dynamics, where we have these small excitations, actually our strain levels will be very small. What we see is that with in the dynamic range, we'll have very high stiffness compared to the more sort of common engineering stiffness properties. So that's something that you have to take into account while doing your analysis. Typically, people get this value from the shear wave velocity. And then we can determine the shear modulus using Hooke's law. Can then transfer that to the Young's modulus. You can tweak that yourself, but typically in Plaxis we have the HS small model that will take that into account based on a stiffness degradation curve based on the shear strain. So that is then automatically taken into account. It also has some additional effect, nice effects, as that will also include material damping, high hysteresis effect, those kind of things. So that can lead to damping. So So that's also something we did not cover here yet. Damping, we have different damping parameters. Material damping, so that's one that's specified by the effect of cyclic loading in the model. So the model should have this. If you have the hardening soil model, material damping is not included. If you have, for instance, the HS small model that takes into account the small strain stiffness, there it's included. We can always specify Rayleigh damping, but that's based on frequency. With numerical damping, so based on the integration scheme, we have different ways of damping these. And another big source of damping is, of course, plasticity. So once the model has plastic deformations, we will lose energy there, and so you'll also have damping in those kind of things. One important note here is that damping is nice, but if you overdamp the solution, it may lead to non-conservative results. We will have less displacement, we have less forces on our structures. So that's something that you might want to get from your analysis, which you did not see if you have overdamped the system. Dynamic liquefaction is also something we did not talk here, but in order to use liquefaction models, we have to make sure that we have a model that takes into account liquefaction. So it's accumulation of excess pore pressures that can lead to a reduction of effective stresses, so that can then lead to instability. So for typical models that we have in Plaxis, we have the UPC sand model already available for some time. It's available in Plaxis 2D and Plaxis 3D. We have PM4 that's a 2D model as the original model from UC Davis. And soon in the upcoming release, we're also going to introduce PM4 silt, also 2D only model to stay true to the original implementation from UC Davis. So UPC sand liquefaction in 2D and 3D, PM4 sand and PM4 silt liquefaction in 2D. Last but not least, finite element mesh. The element size and the wave velocity combined will lead to a critical time step. So choosing your mesh size is important. The idea here is that the wave should not travel more than one element in a single time step, because if the wave should travel over more than one element, actually you will lose information because the information goes outside a single soil element. So the element size and wave velocity determine what your critical time step is. So it should not be larger than this critical time step. So that puts some restrictions on the time step that you can use. Element type also plays a role here. If you use 6-noded or 15-noded elements in Plaxis 2D, it can have some effect. It has an effect on critical time step. But also when you have higher order elements, as the 15-noded element, also you will see less numerical dispersion. A side effect of this is if you want to use a finer mesh in your calculation, it may lead to longer calculation. And the simple reason is if you use a finer mesh, then we have more elements in your model, and it means that for a single time step, we'll have to calculate more nodes, more equations. So it will take a bit longer time for each calculation time step to do so. So if you then have 2000 calculation time steps that you want to do, you have to increase the calculation time for all these 2000 steps. But also, what actually is more concern is that if you have a finer mesh, it will mean that our critical time step has to go down as well. And then when the critical time step goes down, it also means that we will need more calculation steps in the analysis. So actually, when making the mesh finer, actually you're going to increase the calculation time quite dramatically if you are creating too small elements. So these are some important topics that we did not cover today, which I wanted to mention to make sure that you at least understand these effects here. To summarize what we talked about here today, we talked about dynamic loading, so applying loads or distributed loads. So how to define a dynamic load using static and a dynamic component, and the dynamic component consists of a load value times multiplier. And for this one, once the source is inside the model, we can use the viscous boundary conditions. If we have a seismic or earthquake event, the boundary conditions that we have to specify should be free field elements and a rigid base. Or if you use a 1D site response analysis, so just a single soil column, we can use the tight degrees of freedom. If you have an accelerogram, you can directly specify this in Plaxis using prescribed displacement, using these multipliers, and can apply drift correction to make sure that any errors, small errors during the from the accelerogram are actually a result in a zero displacement. And important time stepping should match the data points. So it's something to take into account while specifying your time steps. Before we come to the questions, I want to invite you to the g2.com website, which is an independent software review website where actually there's a peer-reviewed software there. So you can actually see people reviewing the Plaxis 2D and Plaxis 3D applications. And we also invite you to do so. There's now a nice incentive here, is that while doing a review for Plaxis, and it's on g2.com, which is independent from Bentley or Plaxis, so it can be a positive feedback. Of course, we always hope for positive feedback, but if it's negative, you can also put it there. You also then will be eligible for this $10 donation for the charity called Water for People. So that's an organization that will that its goal is to improve uh, drinking water for a lot of people around the world. So that's also important for people to stay healthy and to stay safe. So if you write a review here, which takes about 7 to 12 minutes, then there will be a donation, and also you help us by adding a review here. So let's go to the questions. But before I go to the questions, I also have a resource list, and I'll show the resource also here in the chat. So in the chat, I put the link to this Plaxis 2D and 3D review on g2.com. I really invite you to do so we can increase also the donation fee there. And the resource download, which is basically a download of this page that you see now on your screen. And yeah, so we have all the topics that we talked about today, about some features, how to set tight degrees of freedom, for instance. Two very nice articles that we have written here by Anita Lera and Ronald Brinkgeven. It's the ground response analysis and the site response analysis and liquefaction evaluation. You can find a lot of details on how to specify the signal and how to deal with damping for two specific cases. So the resource list is available in the chat, so you can directly click on the link there and download it there. So now it's time for some questions. I see I'm exactly on time for the presentation. I still have about 10-15 minutes left for questions. So if you have questions, drop them in the questions part, not in the chat, because then I cannot really see what I've answered already. See a question here, why not set substeps is 1 and max step is number of acceleration points? I think that's a, so the question is about, let me see, where's this one here? I think that's a very good question. So the question was, why should we not set the number of substeps to 1 and the max steps to the data points that we have? Now, yeah, sure, you can do that, and especially want to make animations, or if you're not sure about all how you want to do the post-processing of the analysis, that might be a very good idea. It will also generate a lot of data on your computer. Plus the max steps that we have, it's limited here to 10,000. So if you have more than 10,000 data points, it will not fit in having this as 10,000. So then actually, then you also have to use the number of substeps. So it's also a matter of data points which are completely stored and can lead to a lot of data, especially when doing dynamics in, for instance, 3D, then the data can be so much that you really have to take that into account by getting hundreds of gigabytes of data on your computer. So that's also something to consider while choosing this. If you just do everything, it will generate a lot of data. All right. Question from Bare. Can you describe what boundary conditions should be used for outcropping versus within motions? So I hope I answered that question already. So if you have a motion which is happening inside the analysis, then you can have the free field elements, and basically seismic events. It's always the preferred way to have the upward motion at the base of the boundary, and then that moves upwards. At the time construction stage, is it reliable to consider for 2D seismic analysis 150 to 180 meter deep tunnels? I think that's a very good question. Having such deep analysis and at such depth, yeah, you have to make sure that you specify your tunnel in such a way that the I have to how to rephrase this. So when you have your tunnel, actually, yeah, you must make sure that you put your boundaries far enough away such that you can have the upward motion still coming downward using compliant base, having free field elements at the side, and depending if there's something which can have a lot of reflections for waves above your tunnel, you might want to include soil layers above, and maybe then yeah, you can also then choose to apply viscous boundaries above if you do not include surface level. But that's, I think, a tricky case when you have such deep tunnels, how to model that. Right, I've not seen anything like that from all my time looking at these models, but I think a very fair question, and also that's something that indeed you should consider, like have the earthquake motion also coming in upward motion, and then have viscous bound at the top to absorb the energy there. What boundary conditions should I choose to impose within motion? Should I use the compliant base with high stiffness? So if you have, so I imagine with that you mentioned that, let's go to, maybe I can go to, let's go to this model. I think that probably answers your question. So say that we have our bedrock motion. So let's assume we have the um, bottom here as bedrock. So this light blue area is bedrock. Otherwise, we cannot model such a shallow model anyway in finite elements. Then we have to extend it deeper. But we can, let's say, we assume that this bottom is a bedrock. The best way to model this is to have the bedrock signal here applied at the base, which is within the bedrock, and then also include a transition from bedrock to the softer soils. Because what happens if you have this upward motion, which of course is the signal coming from deeper layers, if you then get this, maybe due to the stiffness contrast between these the light blue and the orange soil layer in this case, you might already get some reflection back downwards. In order to take that into account, define the bedrock here, and then you have the proper transition from these waves into the softer soils, and that can also give you a better representation and better analysis. So I hope that answered the question. Johannes asked a question regarding the compliant base boundary condition. It's stated in the manual that the input signal should be multiplied by a factor of 0.5. I have to admit, I don't understand why. So if we go back to, let me get back to the, so here we are. So say we have our rock outcropping motion. As I mentioned before, say that you have a rope that you just going to have some kind of harmonic excitation. You will see that you will get this nice sinusoidal function over the rope. But at the end, you will see that the amplitude will be twice as what you have along the rope's length. That's also what you should think about with these compliant base boundaries, is that we have an input motion, which is the upward motion. So that's basically the what you do with your hand with this rope. That's the input motion. But what we have on the as a signal is usually the outcropping motion. So that means that the amplitude will be twice as much. So in order to get the proper upward input motion, actually we have to specify this outcropping motion from this part with 0.5 to make sure that we have the proper amplitude here for the upward motion. Mike asked the question, is hardening soil suitable for dynamic analysis? If you're going to do dynamic analysis, I would use the HS small model, so the hardening soil with small strain. That model is more suitable because it takes into account the change from a high stiffness at the very small strains to a bit softer behavior when we have larger strains. So it has a stiffness degradation curve based on the shear strain. So with that, we can have proper hysteresis effect. So we also have some kind of analysis. So that helps. What's the advised geometry limits for the dynamic analysis or earthquake analysis? So if you think about geometry limits, say we have here our building and we have to choose, okay, how far do we have to go down and how far do we have to extend the model boundaries to the left and right. You have to put your boundaries further away than just from a static analysis, simply because waves travel back and travel all the way to the boundary, and they might reflect on the boundary and then travel backwards. So in order to not have such an influence on your analysis, you must place your boundaries sufficiently far away. If you have a, say that for, if we think about the slope width, so if an embankment with a slope width, usually we take the width of the embankment, and then that should be at least for a, have at least 2 or 3 times the width of this embankment to your model boundaries. For dynamics, you have to, instead of having this factor 3, go to a factor of 5. What I always try to do is that I will measure some points here on the surface. So I'll put a few points here on the surface, and at the end I will plot the accelerations in time or the deformations in time here. And then when I see that there is no additional influence anymore from this element here to the boundaries, and also that doesn't really make any difference near the boundary, then I can assume that the boundaries are far enough away. Comes a bit with experience how far to put them. So if you're not sure At the end, I would always recommend to do a sensitivity analysis by putting the boundary further away. Does it influence your results? If not, then you have placed the boundaries far enough away. But that's something that you also have to invest a bit of time to gain that experience. All right. Abderrahman asked the question, what do you mean by overdamping? And I think I mentioned something here on, let's see, where's the slide? Yeah, something on the part that we did not cover today. I think you referred to, not to overdamp the solution. So if you apply too much damping, and it can mean that you did not tweak, for instance, for the HS small model, that you did not tweak the small strain parameters well enough, where we have the hysteresis damping, or actually that you have the too much Rayleigh damping. And this is something that you also specify in the material data set. So this is a frequency dependent damping. It's not constitutive material damping, but it's a frequency damping in the material. If you put this value too high, or you put the frequency ranges incorrectly, you might put too much damping in the system, which means that if the waves travel through your system, they will be damped too quickly. And if they damp too quickly, maybe, for instance, your earthquake signal does not reach the soil surface properly. And it means that the structure that you have on top of the surface might also not get as much excitation as you would have with proper material damping. So then you can get conservative results because your structure or your slope will have less deformations and accelerations and less earth stresses acting on your structure, and that can lead to non-conservative results. Because then you just think it's safe, while actually the forces in your structure are much higher. So that's something that you have to take care of. And for those kind of things, I always recommend to do a 1D site response analysis to see how the waves travel through the system and to see what's happening at the soil surface, and then if that is okay to do. All right. I also answered that one already. Question here also, sometimes we see that we have very high displacement at the free field boundaries. What causes this? So maybe I should get an image showing the model here. So say that we have this model and we have a large earthquake event. And the question is that you will see large deformations here happening at the model boundaries. What can happen is if the excitations are such that actually the soil stresses reduce in this area here, and that can be because of the that the soil node here wants to move here to the left, while the free field element here wants to move to the right, and that can happen because there's something happening here in your main soil body, and it means that the soil stress will decrease. But say that you still have a high shear stress, actually you can reach the Moore column failure criteria, for instance. And in that case, what will happen is, maybe can I draw this one? So say here we have something in PQ space or sigma tau, doesn't really matter. Say this would be our frictional failure envelope. Excuse my not so straight drawing here. Say that we start with a stress state here. But due to the seismic event, actually we get unloading behavior. So this will move in this direction. And that means actually, so I can move this one here. So that means that we're actually here touching the failure envelope. And that means we'll have plasticity, and so we will have large deformations there. Now this can happen when we have low stresses in fractional materials, or when we generate excess pore pressure on the boundary. And then we can also have this effect that actually, because we develop excess pore pressure, so I should make sure this is effective stress and effective mean stress, we can also then get into this point. Now, the key in this is that it might not be that bad that happened, because with plasticity we will have damping there, so that means that the wave will it will not reflect back into the main domain. So it will go here, it will lose its energy, and it will not come back into the main domain. So if you put your boundaries far enough away, it will not have an effect here on the main domain. So although it looks weird, in not all cases it's a problem. So that's also something to check. What we can see, if what sometimes happens, what you sometimes can do to prevent this, if the boundaries are a bit further away, instead of having undrained soil behavior on your model boundary, just use the same properties but with a drained configuration there, to overcome the generation of very high excess pore pressures. So that can help. Or if the permeability of the material is high enough, you can also use the dynamics with consolidation type of analysis for those kind of things. So that means that the pore pressures cannot go to the very extreme values, and there will be more as you would have them in reality, just by having these dynamics with consolidation analysis. If we consider the same boundary conditions for a variety of soil medium, yes, you can just use the same boundary conditions if you have different soil medium. So if you have clay and silt, and all boundary conditions can handle the same. You do not have to apply something different, because the dampers that are part of the system, they also take into account adjacent soil material. So that also takes into account, and also the free-foot elements take into account. So the free-foot elements here, they take into account. Free-foot elements here take into account the adjacent soil, so it will take the same properties. So that's perfectly fine. Let me see. I still have time to one question. Question from Mike: what is dynamic analysis with consolidation? So in the latest Plaxis version, or actually it's already there for I think a year now, we have an option. So in early versions, you can just use dynamic analysis, and then either the material will be fully drained or fully undrained. So it will be either do not generate excess pore pressure, or it would consider it to be completely undrained, so no volume change possible. But of course, in reality, and especially if you look, for instance, at gravels or coarse sands, while having a dynamics analysis, you might still see some kind of consolidation effect for this type of event. If you think about the hydrodynamic time, which is of course a factor of the CV value, but also the time of the loading. So even if we have high permeability but very short loading times, we can also see undrained soil behavior in, for instance, sands. And you can see this when we have liquefaction, where you have also an accumulation of excess pore pressure in this time. So we introduced in Plaxis also dynamics with consolidation. So that means during the earthquake events, we can also dissipate a bit of excess pore pressure. So that can also make a small difference on the analysis, while not having sort of sometimes very extreme peaks of excess pore pressures. These are then also reduced during the analysis. All right, I see I am at the end of my time here. So I would like to thank you for still being here with me all this time, even after the original hour has already passed. So thank you for staying on so late and so long for the additional questions and answers. I will see if I can answer your questions which you asked here by email. So that should be happening hopefully within a week. I still see I have still a lot of questions open. It might take some time, but I will see that I will answer all or most of them. So while closing out, make sure to check the resources. I will put them in again in the chat list. So you can download them here. One thing to note, next month, SIG on February 9th, we'll do something on automated embankment construction using Python scripting. We'll do a very long road embankment. We have multiple cross sections with varying ground conditions, and then make an automated script for that to make things more efficient, but also to generate all the details required for proper assessment, both for stability and settlements over the entire road profile. So that's happening next month. And I'd like to thank you for your time. Also, thank you for the questions, which means that a lot of people have interest in this topic, which is good for us because then we know that actually the topics that we put forth here are useful. So thank you for your interaction here. And I will see if I can pick up all the questions that we have here. All right, thank you for your time, and I hope to see you next time. Enjoy the rest of the day or the rest of the afternoon or morning. Thank you for your time, and hope to see you next time. Thank you.